going to spend a little time to step through a little algorithm for how to solve problems in a physics class. The best way to learn physics is by solving problems. Um, Compared to other science classes you may have done in the past, where you can read the book and remember everything about the Krebs cycle and be able to draw it all out and remember your various rules for chemistry. Physics is not a science that really works that way. Reading the book on its own is a great thing to do. It's an important thing to do, but it is not going to get you to where you need to be. You learn physics by trying to solve problems. Um, and that really helps you figure out what parts in your mental framework for physics uh, have problems that need to be corrected. And without that feedback cycle of trying to solve things and trying to do things in physics, you're really going to be lacking. Your mental infrastructure is not going to grow without exercise. It's not going to get stronger without that practice. Um, so solving problems is very, very important. And simultaneously, I completely recognize very frustrating. It can be very frustrating to just stare at a physics question and have no idea what the heck to do with it. So this is here as a series of steps. So you have a structure to go back to when you're stuck. Um, so first, make sure you read through the problem all the way to the end. Don't do anything, just read while you're doing it. Go back to the top, read again, one sentence at a time now, and try to sketch what the problem is saying. You have a tremendous amount of your mind dedicated to visual thinking. Try to harness that capability. If you can draw a picture of what the problem is about, you are in a good way along the path to understanding what the problem is asking for. And that's going to help trigger how to solve it. Step 3 is about data collection. Uh, you want to make an inventory of the information that's in the problem. And you'll get used to this over time, but there are going to be some things that are not explicitly stated. You're not going to necessarily say that, um, you know, an explicit statement would be the mass of the object is 5 kilograms, which would tell you I have a variable m and it takes a value of 5 kilograms. That's fairly straightforward. There are other things in physics that are implicit assumptions that then tell you that one or more other things are also true. The object moves in uniform circular motion. It's going to be an example that we'll cover. You can ignore air resistance. The object rolls without slipping. Um, these are statements that have very specific meaning in physics and tell you valuable information. So it's entirely possible that the problem would not be solvable without those statements. And then sometimes you're not given a value at all. This is famously done with the mass of an object, because many times the mass is going to cancel out. And if a variable you think should be there doesn't have a value, just leave it as a variable. And if you do things correctly, you should find that it cancels out on both sides of your equation or equations. All right, so you've read again, you've done an inventory. Now, what do you think you're actually being asked to do? What is the thing that you're being asked to solve for? And as you formulate what you think that is, um, check with yourself, is this something that I could get an order of magnitude estimate for how big the answer should be? So once I've gone through and solved things, can I say, well, this is reasonable, at least matched my expectation for how big this value should be. If you come out with a force that's 1,000 times smaller than the weight of a snowflake, it's probably not a force that you're going to be able to experience physically in everyday life, because it is far, far too small. So think roughly to what power of 10 you would estimate the answer to be, and then put that aside and use that later once you have an answer. All right, so now we know what it is we're being asked for. This is putting together a plan here in step 5. What relationships and physics might be relevant? What, given your inventory and what it is you're ultimately being asked to solve for. So you want to put together essentially like the recipe or the plan. These laws of physics involve the knowns that I am given or can assume from the problem statement, and the unknown or unknowns that I'm trying to solve for. This is where, like, at least starting off in physics, people will struggle with a bit. Just because there's an m in an equation doesn't mean that that is going to let you solve for what you're trying to accomplish. Okay, so you need to be patient. Step 6, this is one pretty much every starting physics student has some trouble with. Don't put in numbers. Okay, you have a plan because you finished step 5. Don't put in numbers yet. Leave your equations as algebraic expressions, as mathematical statements without numbers yet. And do whatever arrangements you need to do with your equation to get your unknown on one side and everything known on the other side. Or it could be a system of equations where you're going to have to do that to get a solution for each of the things you're requested or that you need to find. But once you substitute in numbers, it tends to lose meaning. It is cumbersome. It takes a long time to write it out. Just don't. Just leave it as a single variable or a variable with a subscript. And that's going to be much quicker and easier to work through. So you have a plan. You've manipulated your equations in algebraic form. Now you execute the plan by taking your final equation, then put in the numerical values. Then you go to a calculator if you need to, and you come up with your answer. Once you put in numerical values, you should also substitute in the unit that each of those values is measured in. So mass is in kilograms, time is in seconds, or you could have a compound unit that is some combination of MKS values. This is important because your answer has to have the right units. The left-hand side of an equation has to have units that match the right-hand side of the equation. And if they don't, you must have made at least one error. If the dimensions on both sides agree, that doesn't mean you're right. But if they don't agree, you're definitely wrong. And this is a great way to catch errors. All right. And then we have an answer, we have a numerical value. Now we go back to our order of magnitude estimate for how big it was, how big we thought it should be. Did I learn something from this problem? Is my answer reasonable? Is it the right order of magnitude? Is it measured in the right units? Does it have the right sign? If it's a vector, does it point in the right direction? Does it match your intuition? And you can do a little bit more analysis at this point. If you want to go deeper into the problem or think more about it, go back to your algebraic expression and check it to make sure that it agrees with your intuition. If I take the variable m in Newton's second law of motion, F equals ma. If I take m to go to infinity, so it has infinite inertia, then that should intuitively tell me that it's an immovable object, right? It can have no acceleration for any finite force, right? And you can also take the limit where the inertia goes to zero. So m becomes very, very small. And that is going to tell me that I will have a whopping large acceleration as long as the force applied to the object is not zero, because I'm essentially dividing by zero. All right. So if you get stuck, if you don't know how to proceed, and that's going to happen inevitably over the course of learning this subject material. And this is a series of steps that you can think of as an algorithm to go back to, so you have some sense of what to do next. What's the process of trying to solve this problem?